let's talk a little bit about that delta S and things we can do to either get that number or think a little more about predicting whether that's going to be positive or negative. Okay? Standard changes can be calculated for any thermodynamic property like delta H, entropy change, or Gibbs free energy change. Okay? So we use the little superscript 0 or degree sign. It depends, some kind of little circle or oval superscripted next to the state function just means that we're in standard conditions now. Okay? So those standard states are 1 atmosphere for a gas sample, 1 molar for a solution, or a pure liquid or gas in its pure liquid or I think it's gases are 1 atmosphere. Here, put solid here. Okay. Already talked about 1 atmosphere for gases. Okay? Pure liquid or solid in its most stable room temperature form. Okay? So the elements on the periodic table, most of them are solids. Okay? 2 are liquids at room temperature, mercury and bromine. Right? Gases are the noble gases over there, as well as a couple of nonmetals, right? Especially in the top row, nitrogen, oxygen, okay? Fluorine, chlorine. So that's what we're talking about, room temperature, okay, for elements. For other things, you might have to look it up. For ionic compounds, they're all solids, right? All ionic compounds are pretty much solids. For molecules, you would probably not know unless you knew its boiling point or something like that. So here's the third law of thermodynamics. We talked about first law and second law, I think, already. The third law is that the entropy of a perfect crystal at 0 Kelvin is 0. Okay? So because we have an actual starting point for entropy, we can talk about actual entropy values. There is no such thing as an enthalpy value. Okay? Because heat is only ever transferred into or out of something. There is, you can't really think, hey Ben, welcome. You can't really think of something with like 0 heat to it. It's different from absolute 0. It's always a into or out of type thing. But a perfect crystal has 0 entropy because there is only one possible way for that to be. Okay? If it's at 0 Kelvin, it's not moving. It's motionless. So there's no rotational, translational, anything like that. And if it's a perfect crystal, there are no gaps or anything like that. There's only one way for that to be, so that's 0 entropy. Okay? But that's pretty much the only way to have 0 entropy for something. Okay? So because of that, and because you can calculate entropy changes, it's possible to have specific entropy values for things, because we have that sort of starting point. So we can use that to compare the entropy of just a particular phase of a substance. But again, it's the same comparison that we've been talking about. Is energy being dispersed in that system, or is energy being concentrated and kind of compacted in that system? Okay? So what would have the highest entropy of a substance? Gas, the liquid, or the solid? Yeah, the gas would. So let's do gas greater than liquid greater than solid for a particular substance. Okay. What if you're comparing 2 substances where everything about them is very similar except their molar mass? Correct. For a couple of reasons. It's probably mostly electronic. More electrons means more possible electron arrangements. Okay, that's one. Also, the larger something gets, especially if it, I won't do molecular complexity. Here, simplest example would be just an atom, a low molar mass atom versus a high molar mass atom, right? An atom of hydrogen versus an atom of iodine or something like that. Okay, so it's not in terms of complexity. It would mostly be in terms of electrons and electron configurations. If you saw the, remember first semester, the atomic emission spectra, right? That the colors of light that are given off by those electron transitions. Okay? The smaller an atom is, it has a couple of lines given off, but a big atom has hundreds of different lines given off from all those electron transitions. So that's a good example of that. All right, argon and NO, nitrogen monoxide. Those are two molecules that I picked because they're about the same in molar mass, but this is monoatomic, that is diatomic. So what do you think? The diatomic would have greater entropy because now, in addition to there just being electrons flying around, there is now the relationship of position of these two atoms relative to each other. So molecules themselves actually have vibrations to them. Every covalent bond vibrates in some sort of way. That's the theory behind all kinds of spectroscopies and things like that. So molecular complexity. What if we have a solid sample versus that same sample dissolved in water? Yep, absolutely. For pretty much the same reason that we put liquid higher in entropy than solids or something. With a solid, it's all stacked up nice and neat. When either it's melted or it's been dissolved in something, it can be going all different directions. There's all kinds of different ways that it could be described. Okay? So, here, I'm just going to put high entropy, high entropy, high entropy. There.
This all matches up with what you said in your video about large number of molecules.
Absolutely. Yep. Absolutely. Here, did we talk about that?
You talked about it in your video the other
Yeah, that seems right. Going from.
if you have a lot of cells or something.
Yeah.
Increase the entropy, I thought I heard.
More dispersed, more dispersed. Entropy is the dispersal of energy. Yeah, I talked about this somewhere, but let's just write that here just in case, right? 1 mole is something 2 to 2 moles of something, right? Or let's say 1 mole of A makes here. How about just 1 A makes right, something like that, where we got 1 mole total here, but we got 2 moles. Okay. So we got higher entropy there. And that's actually a very common driver of entropy in chemical reactions, when one substance produces multiple products like that. When something breaks apart like that, that's an immediate giveaway that entropy will be increasing. So delta S would be positive for something like that. Okay? So I don't know where we talked about that, but it makes sense there too. All right. So if we have absolute entropy values for all the substances involved in a reaction, we can calculate the delta S overall for that reaction, very similar to how we did delta H's in first semester. Okay? So the sum times the coefficient of all the products minus the sum times their coefficient of each of the reactants. Okay? Right? The sum of the coefficient times the entropy of all the reactants. So it's always products minus reactants. Okay? So, for instance, in this reaction I've got written down here, N2 plus gas plus 3H2 equilibrium 2 NH3. Okay. So just based off of number of moles of things, and especially since they're all gases, we don't have any condensing happening here, would you predict this to be an increase or a decrease in entropy, going from reactants to products?
A decrease.
Yeah, this would be a decrease in energy, right? Our prediction, delta S would be negative. decrease in entropy. Okay. Just by comparing how many molecules there are on the reactant side and product side. Okay. So that would be our prediction for that. We start with 4 moles of gas floating around. On the product side, we get 2 moles of gas. Okay? That would be a concentration of energy as opposed to a dispersal of energy. We can calculate the actual value, though, under standard conditions if we have absolute entropy values for them, which can be looked up in the appendix in your textbook. Okay? So, 191.6, 130.6, 192.7. Absolute entropy values are usually given in joules per mole Kelvin. We'll see in a second why that unit is what it is. But we can then calculate standard for the reaction. It would be, what would we do first? Yeah, so let's start with the products. So we do 2. And one way of thinking of this is have that coefficient be moles. 2 moles of that times 192.7 joules mole per mole Kelvin. What that does is cancel out the moles. Okay, so that's all we have for the products. So then it is minus, and then I usually like to put a big square bracket and say, I'm not going to include the units anymore, but 191.6 plus 3, 130.6, like that. But it's the sign that gives students more trouble than anything in this. Okay? All of us are pretty much capable of multiplying coefficients by a looked up number. It's that sign that you have to really watch out for. So either get this number separately and then do that minus that number, or do minus and then parentheses around that whole thing in your calculator, or distribute the minus. That's distributing the minus is a little more dangerous. That is kind of asking for transcription issues, especially with delta H values that can be negative. Okay? Entropy values are always positive because we start at 0 entropy for a perfect crystal. Anything else has more entropy to it than a perfect crystal. Okay? Anybody get a number? Yep, that's what I got. And if we did this kind of thing in the calculation, what would the unit for entropy change of a reaction be? Joules per Kelvin. Okay. And so, yes, our prediction was correct. Okay. Especially for similar size gases that have relatively similar entropy values. The main determiner in here was those coefficients. Okay. Prediction of entropy decrease was correct. Okay. All right. No, not at all. Not at all. Entropy change and enthalpy change are pretty much completely independent of each other. We talked about the four ways that you can have it: negative, positive, positive, negative, both positive. Okay. So, yeah. the